So we have done enough theory with magnetic vector potential, and we saw how vector potential can be calculated if the current distribution is given, or if magnetic field is known, then how we can get this vector potential. All those things we did. We had this choice of divergence A equal to 0. Traditionally that is taken as a choice because as such A is not unique. So with those, in this lecture I will be solving some problems, and our first problem is this. The vector potential in a region is given by A vector equal to R vector cross C vector, where C is a constant vector and R is of course the position vector. Find the magnetic field in the region. So if A is given, finding magnetic field is straight. B is equal to curl of A. B is equal to curl of A. That is the defining property of this vector potential. So if you know the vector potential, you only have to take the curl to get this B, and this we can do in Cartesian coordinates, simple. So A is equal to R and cross C, R and cross C. So curl of A is curl of this. So first let us write this in Cartesian coordinates. So this is this cross product and vector, right, vector and vector, cross product of two vectors. So it will be the three components of this, the three components of this will go in the second and third row, and the first row we will have I cap, j cap and k cap. Second row we will have this, the x component is here, the y component is here, the z component is here. So x here, y here and z here. Remember, this r vector is a position vector, x I cap plus y j cap plus z k cap. So x component of this r vector is x, y component of this r vector is y, z component of this r vector is z, and ax is x, ay is y, az is z. Here we write ax, here we write ay, here we write az. And then the second vector a cross b, I am talking in terms of the vector multiplications a cross b. The second vector, the three components of the second vector will go there. So suppose this is a constant vector, so this will be some c1 times I cap plus some c2 times j cap plus some c3 times k cap, and these components will go here c1, c2 and c3, and this is equal to I cap, this is equal to I cap. So mentally omit the first column and the first row, the one containing this I cap, the one containing in this I cap. So mentally omit this, mentally omit this. You have this 2 by 2 matrix. So y into c3, y into c3 and minus z into c2, that is I cap, j cap. Mentally omit the row and column containing j. So omit this one and this one. So you get x, z, c1, c2, but you have to come the other way. So this z c1 first, z c1 and then minus x c3 and plus k cap. Omit this k cap containing column and k cap containing row. You have these four. So you have x c2 and then minus yc1 minus yc1. If you can write 1, the others one can be written as cyclic permutation. So I cap here, j cap here, y here, the next one is z, c3 the next one is c1, z the next one is x, c2 the next is c3, and similarly from here to here, z the next one is x, then c1 the next is c2, x the next is y, c3 the next is C1. So 1, 2, 3, 1 and then 2 and then 3 and then again 1, 1, 2, 3. So 1, 2, 3 and then 1. So that is the cycle. So that is why it is called cyclic permutation. So these are the components of what? Of what? Of this AX. So AX is equal to YC3 and minus ZC2. AY is equal to, this is AY, ZC1 and plus XC3, and then Z is equal to XC2 and minus YC1. So these are the three components of the magnetic vector potential. Now come to this, B is curl of A. So B is equal to curl of A. This is again the vector product rules one can use to write this. This is I cap here, j cap here, k cap here, this first row same as this, and then here we wrote the xyz components of this first vector. Here it will be not components, but we know why we are writing this. This will be del del x, this will be del del y, and this will be del del z. And then the three components of this A. So that will be Ax. What is Ax? Ax is y C3 and minus ZC2, ZC2. Then the y component will come here, and that is here Z C1 and y plus, it has to be minus, everywhere it is minus. So ZC1 and minus XC3, and the Z component is XC2 and minus YC1. So let us evaluate. Start with I cap. How do we open this determinant? We first write this I cap and then mentally omit the row and the column, this column and this row containing I cap. Mentally omit these two. Then you are left with this and this. Then del del y of this minus del del z of this. So how much is del del y of this? Just think of this. Differentiate with respect to y. Differentiate with respect to y. No y here, no y here. So this term gives you 0. And differentiate with respect to y. This is constant. So this will give you minus 1 and C1. So it is minus C1. So it is minus C1. What did we do? Del del y of this minus del del z of this. Okay. So now minus del del z of this. What is this? Del del z of this. So minus del del z of this quantity is C1. So it is C1 here, and no z here, no z here. So it will be 0. J cap. Come to j cap. So mentally omit this j cap row and mentally omit this j cap column and this j cap row. So what you are left with? If you omit this, you have this, and this. But then you have to start from here, cyclic. Del del z of this and minus del del x of this. So how much is del del z of this quantity? This quantity. Del del z of this quantity. Differentiate with respect to z. 0 here, no z, no z. Then minus, and this is z here. So it is minus C2. Differentiate with respect to z, you get minus C2. So you get minus C2. We have done del del z of this. Then we have to do minus del del x of this. So differentiate this with respect to x. Differentiate with respect to x, you get C2 from here and 0 from here. You are differentiating with respect to x. So C2 here and 0 here. So it is minus C2 plus k cap. plus k cap. Omit this row which contains k cap, omit this column which contains k cap, you are left with these 4, this one, this one, this one, this one. So, del x of this, how much is that? It is minus C3, it is minus C3, and minus then del y of this gives you C3, it is this. So, how much is this? This is minus 2 C1, this is equal to minus 2 C1, see, minus 2 C1 I cap, and then what is j cap? Minus 2 C2 j cap, minus 2 C2 j cap, and then minus 2 C3 k cap, minus 2 C3 k cap, which is, if you take minus 2 common, it is C1 I cap plus C2 j cap and plus C3 k cap, and therefore it is minus 2 times the given vector C. So, that is the magnetic field, that is the magnetic, it is a constant magnetic field in the direction opposite to this C vector, and then you can write all things. So, our next question is, in a certain region the vector potential is A equal to k x j cap. So, Cartesian coordinates are being used where k is a constant. Find the current density here. So, the vector potential is given and we need current density. So, the process is very simple. If this vector potential is given, we can get what is B magnetic field, which that will be curl of A, and then once B is known, then we can use Ampere's law. Curl of B is equal to mu naught times J. So, that will give me the current density. So, simple, curl of A, B. First let us see what is B. B is curl of A, and this Cartesian coordinates. So, you do not need to refer to the book or anywhere else. This is I cap, j cap, k cap, then del x, del y, and del z, and ax and ay and az. So, here we only have j cap, we do not have I cap, we do not have k cap. So, y component is there, x component is 0, ax is 0 and az is 0. So, this is 0. So, this is ax is 0. So, this is 0 here, ay will be there, and how much is ay? How much is ay? It is k times x. So, for this ay you write k times x and az is 0. So, this is that determinant. And then use, how do we open this determinant? It will be I cap, and then mentally omit these 2 rows and column, and then you have this 2 by 2 matrix del y of 0 and minus del z of kx. This is 0 and this is also 0, it is x here and differentiation is with respect to z. So, this whole thing is 0. Then j cap, then j cap, del z of 0 and minus del x of 0. So, if I am writing j cap here, we mentally omit this and omit this, and then these 4 are left, this one, this one, this one, this one, both have 0. So, this is also 0, and therefore, k cap. Now, mentally omit this k cap column, this k cap row. So, you have these 4 here, del x of kx, which is k, del x of kx, which is k, minus del y of 0, which is 0. So, it is just this. So, that is it. So, this k is there. So, you have B is equal to k times k cap. and hence the current density J, which is 1 by mu naught times curl of B, is 0. This is constant. So, the magnitude is constant, the direction is constant, k cap, nothing is changing here. So, it is a constant magnetic field, and therefore, the curl of a constant magnetic field has to be 0, curl, divergence, everything has to be 0, no differentiation because it is constant. So, the current density is 0. And our next problem is on the board. The vector potential in a region is given by A equal to mu naught I z over S cap. Its cylindrical coordinates clear because we are using S cap. Show that divergence A is 0 and then find the magnetic field in the region. So, that is the first part. Alright. So, we are given the vector potential and we have to show that the divergence of this is 0. Since it is given in cylindrical coordinates, therefore, we will have to use the proper formula for divergence. So, that is here in the appendix. This is in cylindrical coordinates, divergence of A is equal to 1 over S delta here, delta S here, and then S A S, and then we have plus 1 over S and del phi of A phi, and then we have plus del A z over del z. So, that is the divergence equation, and we use this thing here. A vector has S component only, S cap. It does not have phi component, it does not have Z component. So, A phi is 0 and A z is 0 first. So, this term is not there, this term is not there, you only have this, and this is divergence of A is equal to 1 by S here, del S here, this S here, and then AS. AS is S component of A. That means the quantity which is here before this S cap, this is the S component. So, this is A subscript S, this AS is here. So, that we will write mu naught I z by S. So, it is mu naught I z by S, and now this S cancels and then it becomes independent of S, and therefore, the differentiation will be 0 and therefore, this is 0. So, that is one. Then find the magnetic field in the region. Now, if the vector potential is given, finding magnetic field is straightforward because that is the definition. Your B is equal to curl of A. So, once again I will have to go to the book and the appendix and look for the curl equation in cylindrical coordinates. So, this is curl here. This is in cylindrical coordinates, curl of A is equal to what? Curl of A is, the first bracket is 1 over S and then del Az del phi, minus del A phi del Z. This is the first bracket, and then you have this S cap, and the second bracket is del AS del Z, and minus del A z del S, del A z and del S. This is the second bracket and it is phi cap here, and the third bracket is plus 1 by S outside the bracket, and then we have del S and S A phi, S A phi, and minus del A z and del phi, del A S del phi, bracket closed, and this is k cap. All right. So, put what is A? A is given by, A is this, so A is mu naught I z by S cap. So, you only have AS, A phi and AZ are 0. So, A phi is 0, so this term is not there. AZ is 0, so this term is not there. A phi AZ is 0, so this term is not there, and A phi is 0, so this term is not there. So, we only have AS, the S component, we only have S component of A, and therefore, all other components are 0. So, this B curl of A, B, this is curl of A, this is curl of A. So, B is equal to, this is gone, and here del AS del Z. So, del Z of del Z of AS, and here is AS, AS is mu naught I Z over S, that is AS, and phi cap, this is phi cap, and then we have this del AS over del AS del phi. So, differentiate del AS, differentiate AS with respect to phi, and AS does not contain phi. AS does not contain phi. So, differentiation with respect to phi is 0. Although AS is not 0, but differentiation with respect to this phi is 0, and so this is also gone. So, that is it. This is the magnetic field. So, this is equal to, this B is equal to mu naught I over S, mu naught I over S, and then this is 1, this differentiation is 1, and phi cap. So, that is the magnetic field. So, this is our part A, find the magnetic field in the region. Now, we come to part B. So, I will erase certain things and I will retain certain things. I will erase this. So, now vector A is given mu naught I log of A by S and in k cap direction. So, A vector is now given as mu naught I ln A by S and k cap, and then the question is, show that divergence of A is 0. So, once again the divergence of A is supposed to be 0. So, let us use this divergence of A. Now, you have k component, this is k component and z component, and therefore, S component is 0 and phi component is 0. And hence, this term will go away, this term will go away, and A phi is 0. So, this term will go away, and therefore, you will have divergence of A is equal to, since this term is gone, this term is gone, it is del Az del Z, and Az is this, Az is mu naught capital I ln of A by S. It does not contain Z, and therefore, if you differentiate with respect to Z, this will be 0, this will be 0, hence this divergence of A is 0. So, divergence of A was 0 for this vector potential, and divergence of A is also 0 for the other potential. In fact, this was our choice. We use vector potentials with this condition that divergence of A is 0, and this calculation shows that we have chosen this vector potential and we have chosen this vector potential according to the convention. Divergence of A is 0. So, both are having 0 divergence. Next part is find the magnetic field in the region. So, magnetic field will be given by this curl of A, and now it is AS is 0 and A phi is 0. So, AS is 0. So, AS is 0. So, this part is 0. This part is 0. And AS this here AS is 0. So, this part is 0, and A phi is 0. A phi is 0. So, A phi is 0. So, this term is gone, and A phi is 0. So, this term is gone. So, what is left? It is 1 by S del A Z del phi, and then S cap here plus, and this is minus. So, let me write minus del A Z del S in phi cap direction, and then this is 0 and this is 0. So, that is it. That is it. Now, AZ is here. AZ depends on S. AZ does not depend on phi. So, this term is also 0, but AZ depends on S. So, that this has to be taken care of. So, this is equal to minus del S of AZ. AZ is mu naught capital I, and then log of A by S, phi cap direction. So, this is phi cap direction. So, this will be equal to minus del S. So, minus mu naught I, and then del S of log of 1 A by S. So, if you differentiate with respect to this A by S, what do you get? You get ln A by S differentiated with respect to A by S will be just reverse of this, that is S by A. And then you will differentiate this A by S with respect to S. That is the rule of differentiation, chain rule. So, first differentiate with respect to A by S. So, log is being differentiated. So, it will be reverse of this S by A, and then this is to be differentiated with respect to S, and that will be minus A by S square. Right, 1 by S differentiation is minus 1 by S square. So, it is that this A is here. So, this minus and this minus they become plus, this A cancels with this A, and S here, S square here. So, 1 by S. So, it is mu naught I and divided by S, and this is all in phi cap direction. Now, this was the magnetic field in part A also. Okay, this was the magnetic field in part A also. So, this vector potential also gives me this magnetic field mu naught I by S phi cap, and this vector potential also gives me the same magnetic field mu naught I by S phi cap, and the choice of divergence A is equal to 0 is also satisfied by this as well as this. And therefore, the third question, for the same magnetic field and for the same choice divergence of A equal to 0, how are you getting two different functions for A? Because we say that divergence and curl, they define the vector field. If you know the divergence everywhere, you know this curl everywhere, but the third thing that is missing is the value of the vector at the boundary. So, this is valid in some region, whatever region, in a region given by, but we do not know in this problem, it is not given the values of A on the boundary of that region. So, a vector to be uniquely specified, you need the divergence and the curl at all points in the region, and also the value of A on the surface of the region. Since that is not given, that is why it is not unique. Okay, so our next question and perhaps the last question is, a sphere of radius r, capital R, has a surface charge density sigma naught and rotates with an angular velocity omega about one of its diameter. We have discussed this situation in our lecture, one of our lectures, that you have a sphere, and on the surface you have some charge distribution, constant charge distribution, and that surface charge density is sigma naught, and then it rotates about a diameter, and this diameter is taken as z axis. Okay, so rotates with an angular velocity omega about one of its diameter taken as the z axis. You have to find the magnetic field at a point with spherical polar coordinate this. The significance of this is small r, this is small r, is 2 capital R, and of course theta and phi are pi by 4, pi by 4. So, r equal to 2r means our point is outside this sphere. This is the point where this magnetic field is asked. Now, in the lecture we had solved in detail how to get the vector potential inside this sphere. So, that we had obtained, and for that, if you remember, we took help of polarized, electrically polarized sphere, uniform polarization, and then the electric field coming from there minus P naught over 3 epsilon naught, and from that we could get this kind of surface charge density, and because of that, what is the potential there, electric potential, and from that expression we wrote vector potential. And we just mentioned it was a homework for you to get the vector potential in a similar fashion. Once you know this charge distribution, for outside it is a dipole, and for a dipole the potential, electric potential is 1 by 4 pi epsilon naught, and then that P to P whatever cos theta by r square. So, using that you can similarly get the vector potential. So, that has been done in the book, and I will take the expression from there. I will take the expression from there, and that is the vector potential A. In this case the vector potential A for outside is mu naught omega sigma capital R to the power 4 divided by 3 r square, and then sin theta phi cap, sin theta and phi cap. So, this is the vector potential. To obtain, you have to do all that exercise of uniform polarized spheres and so on. This is one way in which I solved this problem. Griffiths has done it in a very different manner. So, use this vector potential and get this B. So, to get this magnetic field for a point outside, using this is for outside, this expression is for outside. Inside you have a different expression which was derived in the lecture. So, B is equal to curl of A, but now we have spherical polar coordinates. So, we need the expression of curl in spherical polar coordinates, and once again we have to go for the book and the appendix. Curl. So, spherical polar coordinates, curl of A is given by 1 by r sin theta, 1 by small r sin theta, and then bracket del theta sin theta a phi, sin theta a phi, and minus del a theta del phi, bracket closed, and r cap. This is the first part, r cap part, and then theta cap part will be 1 by r outside, then this is square bracket 1 by sin theta, 1 by sin theta del a r del phi, and minus del r of r a phi, bracket closed, phi cap, and plus the third part, this is 1 by r, once again outside it is 1 by r del r, and then you have r a theta and minus del theta of AR. This is phi, this was theta cap, this was theta cap, and this is phi cap. So, here the vector potential A only has phi component, it does not have r component, it does not have theta component. So, AR is 0, A theta is 0, and A phi is phi component is this mu naught omega sigma capital R 4 divided by 3. This is a constant, and then you have sin theta by r square, sin theta by r square. This is A phi. This is a constant, if you wish you can write as some k, sin theta by r square. K is this, at the end we will put. So, now look at this expression of curl of A, which is the expression for the magnetic field. You only have A phi, you do not have A r, you do not have A theta. A phi is there. So, A phi is there, A theta is not there, omit this. A r is not there, omit this. A phi is there, yes, good. A r is not there, A theta is not there. So, this whole thing is not there. So, you have two components, one component is r cap, another component is theta cap. So, let us write that r component. What is r component? This one, 1 by r sin theta, 1 by r sin theta, good, 1 by r sin theta, del theta of, okay, this square bracket is no more needed, I have only one term, del theta of what? Of what? Sin theta into A phi. So, sin theta into A phi. What is A phi? What is A phi? A phi is here. A phi is here. This is A phi. So, put it here. K times sin theta divided by r square. That is r cap part. This is r cap part. Then you also have a theta cap part plus theta cap. And how much is theta cap? Theta cap is 1 by r, this 1 by r, and then minus here. So, let us write minus here. So, let us write minus 1 here, and then I have del r here, minus, I have already written del r here of what? R times A phi. How much is A phi? A phi is k k sin theta by r square. Okay, so this is our r cap this much and theta cap this much. So let's evaluate. R cap 1 over r sin theta, then k by r square. I am differentiating with respect to theta. So r is constant, k by r square is constant, sin square theta to be differentiated, sin square theta to be differentiated. So 2 times sin theta cos theta, 2 times sin theta cos theta, that is our r cap part, plus theta cap, minus here 1 by r here, and then differentiation is with respect to r. Here is r, here is r square, so it is 1 by r, and k is there, so k also you can write, sin theta also you can write. Since differentiation is with respect to r, sin theta is also to be treated as constant. So this whole k sin theta will come here, this minus is here, this 1 by r is here. Now I have to differentiate 1 by r with respect to r, and differentiation of 1 by r with respect to r is minus 1 by r square. So that is theta cap. Now algebraic simplification, this is equal to, this sin theta cancels with this sin theta, and this k is there, k is there, and then we have 2 cos theta, 2 cos theta, or let me take this k common, 2 cos theta, and then divided by r here, r square here, so it is r cube. That is r cap, this much is r cap. K will be here, from here also I will get k, so k I am writing outside. So this is r cap, this k is here, 2 cos theta is here, this r I have taken care of, this r square I have taken care of, that is r cap, plus theta cap. How much is theta cap? Plus. This minus and this minus becomes plus, so no worry. This k we have already taken, so just sin theta in numerator and r cube in denominator, r square into r is r cube. So that much is theta cap, right. So this is the expression. Neatly you can write this r cube in denominator, and this whole thing is numerator. You can put this k back, k we had written for this quantity. So if I write it here, it is, I can write it as b equal to, and then where is our mu 0? Mu naught is also inside k, right, mu naught, this whole thing is k. So you can write it here, but let's retain it in terms of k. So it is k and then 2 cos theta and plus sin theta, this is with r cap, this is with theta cap, divided by r cube. That is where this capital K is equal to this whole bracket mu naught times omega sigma r4 by 3. That is the magnetic field, and magnetic field is to be calculated at r equal to 2r, small r equal to 2r. So this is k here, and then 2r 8 times r cube. This is small r is, we have to put the values now, it is 2 capital R, so cube of that. Then cos theta, 2 cos theta, theta is pi by 4, so 2 cos pi by 4 is 1 by root 2, this much r cap, plus sin theta is 1 by root 2, this much theta cap. So that is your magnetic field at the given position. So that is all for today's lecture, and next time we will have another chapter.